Today, we're going to start looking at Chapter 6. And Chapters 6, 7, and 8, the focus is on trigonometry. Yep. So, we don't do two-column proofs.
Okay.
No. There will be some things that we prove when we talk about trig identities, but the proofs that we do are not really like a two-column proof. So what I'd like to do first is just kind of look at the word trigonometry and just see what it really means. So let's take a look at it. I want to break it down. Does anybody see something within that word, like a prefix or a suffix, that they might already know what that part means? Yeah? Try. Okay, what does that mean? Three. Okay, so try. Well, that means 3. Anything else? Yeah?
Metry is like measure.
So we have, metry. So that's measurement. So we have that. And how about that part? Gone. What does that mean? Something more specific about a shape. Yeah? Yes, it would be a closed shape. So what would that mean? The word polygon. Poly means many.
But it has many sides.
And gon is sides. The prefix in front is how many.
3-sided measure.
So essentially, trigonometry, if you break that word down, literally means 3-sided measurement. So we are going to be looking at measuring triangles. What are we going to measure? Sometimes we're going to measure the sides, sometimes we're going to measure the angles. But measuring sides and angles is one of the main things we do in trig. So you might look at that and be like, well, why don't they call it triangometry? Well, I don't know. They call it trigonometry. Every polygon has a name for that shape that ends in gon. Some are more common than others, like octagon, hexagon, pentagon. Those are ones we use. Trigon is not normally the name of the 3-sided shape we use. We say triangle, but you can say trigon. Think of like a 4-sided shape. What do we normally call a 4-sided shape?
Square.
You could call it a quadrilateral, but there's another name ending in gon that we don't use as much. Not quadgon. It's a good guess because you think quad is 4. There's another prefix that means 4. Begins with a T. Yeah? Tetragon. So if you talk about tetragons, that's quadrilaterals. And that's why if you've ever played the game Tetris, every shape in Tetris has 4 blocks to it. Because it's tetra, meaning 4. So that's what it basically means. So what can we do with trig? Well, here's kind of a simple kind of thing we can do. Let's say that we were standing right here, and there was some object in the distance. If we knew how far we were from that object, let's say we were 200 feet away, and we knew the angle from where we were standing to the top of that object, which is relatively easy to find if you have the equipment to do it. You could use like a transit if you were surveying property or something like that. But you can get that angle up to there. Let's say it was 30 degrees. Well, we could find the height of that object in front of us, because what we've done is we just basically created a right triangle. There's your right triangle. And we would be solving for x. When you have a right triangle, as long as you know a side and an angle, that's all you need. What gets a little more complicated is let's take that object and instead of having it be perpendicular to the ground, let's have it leaning, like a tower, leaning tower.
Leaning Tower Pizza.
Yes. Does anybody know what the Leaning Tower of Pisa was originally used for? It's, I believe, I have to double check, but I think it was the bell tower for a church. And the church in World War II, I think the roof of the church, it got damaged. I don't know if a bomb went off near it or something, but it damaged the church. But I think the bell tower, the tower was okay. That didn't get hit. So the tower started leaning, and there's a whole story about why it leans. It just wasn't. It's because the ground was really soft, and they didn't build it right. So they tried all kinds of things to fix it, and they've stabilized it for now. But there was a point where it started leaning more and more. Like they could measure it, like at the beginning of the month and at the end of the month, and they could see, like it didn't move like a big number, but it moved enough that if it kept moving at that rate, it would have fallen. So they were able to kind of fix it. I don't know if they dug under it and maybe they put like concrete underneath it, and they kind of stabilized it for a long time. So it won't hopefully fall anytime soon. But if you have a tower, that one's really leaning, and it's leaning like that, and you're standing here, and it's the same basic problem. Let's say you are 200 feet away from let's put it like right there. So 200 feet away from the top of that tower that's closest to you. The problem this time is you don't have a right triangle. So this problem gets a little bit harder. The triangle is right here. And knowing how far you are from the tower and knowing this angle isn't enough. You can't solve that. You need one more piece of information. You either need to know the angle that the tower is leaning at, or if you knew the distance from that green dotted line all the way down to where you're standing, then you could do it. But you need one more piece of information. You always need three. And with a right triangle, you have a piece of information built in because you always have a 90. Now you know. So another kind of problem we can look at related to the last problem would be kind of like triangulation. Okay, triangulation is when you try to find where someone or something is based on using two reference points. So if we had, let's say we had, some kind of fire out here. So there's our fire. And we had two towers that can see the fire. Let's say a tower here and another tower here. As long as those two towers know how far apart they are from each other, okay, so long as we know that number, let's say they're 100 miles apart, and they know the angle that the fire is in relation to them, they can figure out where it is. Okay, it's not that hard. If only one tower could see the smoke, then all the tower could say is, well, I can see some smoke, and from my position, it's at an angle of 23 degrees east of north. But I can't tell you how far away it is. All I can see is smoke. Maybe it's 40 miles, maybe it's 50, maybe it's 60. Well, if they have to know exactly where the fire is, then you're going to need a second tower. And what happens is that tower says, well, I can see the same smoke, but for me, it's at an angle 40 degrees west of north. So together, it's almost like having a laser pointed at the smoke from each tower. They make a triangle, and they can triangulate where that smoke is coming from. You can do the same thing with a cell phone. Pretend like these are cell phone towers. You can measure the time it takes to ping that cell phone, which means send a response to it and let it come back. So you can figure out how far that person is from the cell phone tower. And then if they're in range of a second cell phone tower, you can do the same thing. And by having two cell phone towers, you can triangulate where the phone is. If you have access to that. Usually like a cell phone company could do that. The average person really can't because they don't want you to be able to figure out where somebody is all the time. But for like police or something, that might be a good thing if you were needed help. They could hopefully find you. And it might not be 100% accurate, but it's going to be close enough that it gives them a pretty good idea where you could be. And that's called triangulation. GPS works the same way. The only difference is instead of towers on the ground, it's satellites in outer space. So we'll talk a little bit about problems like that as well. All right, so we talked about what trig means, and one of the most important things we do with trig is measure triangles. So let's start by talking about one of the basic things in a triangle, which is an angle. And even more basic than an angle is just the sides of the angle. Right? We'll talk about what those are called. So an angle is made up of two rays. So you have a starting point. That's a ray. There's another ray. And if you take those two rays and put them together with a common starting point, now you've created an angle. The point that's common to both rays, we call that the vertex. So if you're going to draw an angle all by itself, generally you draw it as two rays. If you draw a shape like that, these three things also are angles. But technically they're not made up of rays. What are the two things that make up an angle in that triangle shape? Yeah? They're line segments. So there's a little bit of flexibility on exactly what makes up an angle. If it's an angle all by itself, it's usually rays. If it's in a polygon, it's line segments. When we draw an angle, it has two sides. It has what we call the initial side and the terminal side. In the angle that I just drew, that's the initial. That's the terminal. And the way you figure out which side is which is you rotate counterclockwise, starting at one side towards the other. Whichever side you end at, that's your terminal. So let's say you drew an angle like this. You're going to rotate counterclockwise between the two angles. This would be your initial. This would be your terminal. That's kind of a weird way to draw an angle. It's almost like it's upside down. There's a standard way that we usually draw an angle. Like there's a certain spot we want to usually put the initial side. You don't usually just draw it randomly like that. This is a little bit more like what it should look like. We usually like the initial side to be horizontal. And it's on like the positive x-axis. So if you think of a coordinate system, you should always put the initial side right there. And then you put the terminal side wherever you want. But if it's not drawn that way, rotate counterclockwise from one side to the other. And the side you start at is the initial, and the side you end at is the terminal. So you move in a CCW is counterclockwise. So you move in a counterclockwise direction to reach the terminal side. Here's another example. In that one, the initial side is almost where it should be. It should be horizontal. It's not quite, but it's pretty good. So the initial side is on the bottom, and if you rotate counterclockwise, you get to the terminal side, pointing up and to the right. Now, in that picture, we really have two angles. What do I mean by that? What do I mean that there's really two angles Right.
You have the interior angle between the terminal and the ignition, and you have the angle on the outside.
Yeah, so we have this interior angle. We also have an exterior angle. Well, most of the time when we're talking about an angle, we're talking about the interior one. We're talking about the shortest path between the initial and the terminal side, not the outside. Any questions on that? Okay, so angles, a lot of times that's going to be what we are solving for. We're not going to know what the angle is. So just like in algebra, we give it a variable. In trig, Greek letters are usually used to represent angles. The reason we use Greek letters is because if you have a triangle, the sides are usually letters we already know when they come from Pythagorean theorem. So what are the sides? What are the letters we use for sides? We use A, B, and C. Now, I know there's no hypotenuse in this picture, but it's fine. Sometimes you'll see textbooks calling the angles capital A, capital B, and capital C. Well, the problem with that is if I ask you, what did you get for B? Well, I'd have to be more specific. Which B? Capital B or lowercase b? So that gets kind of annoying. And the other thing is the letter C, well, depending on if you have other letters around it, you can't really tell if it's capital or not. So to avoid that, we're going to use Greek letters for the angles. And then when we say a Greek letter, we know it's an angle. It's never a side. So there's some of the Greek letters that we'll use. We're not going to use all those today. Just so when you do see them, you know what they're called. Does anybody know what this first one is called?
Fish.
It looks kind of like a fish. Anybody know what it's called? Greek letter? No? Alpha.
That's what alpha looks like?
The lowercase alpha, yep.
I thought it was fish.
All these letters have capitals and lowercases. These are all lowercase letters. So that's alpha. That's the next Greek letter.
Beta.
That's beta. That one looks kind of like a Y, but there's a hook on the left a little bit.
Looks like Aries. No.
Anybody know what that one is? That's gamma. Alpha, beta, and gamma are the three letters that we usually use when we're talking about a triangle. So if I was labeling this diagram, we usually would put A across from alpha, because those are each the first letter in the Greek and English alphabet.
Is alpha like an open-ended sign, or is it more like an A?
Like that. That's alpha. B goes across from beta, and we'd usually put C across from gamma. We're pretty far from labeling triangles, but I'm just showing you where alpha, beta, and gamma are used. Usually when you're drawing a triangle. We're not doing anything with triangles quite yet. We're just talking about angles today. That's all. How about the fourth one? You know what that one is, yeah?
Is that theta?
That's theta. Yep. And the last one, it looks kind of like a W, but it curves in a little bit and it loops on itself in the middle.
Is it omega?
That's omega. That's lowercase omega. If you're wondering, well, I thought omega looked kind of like a horseshoe. Well, if you're thinking of this one,
Yeah.
that's capital omega. Not a Greek letter that we really use. But if you do anything with electrical, that symbol is used for resistance.
It is.
Or does omega have like the open space in the middle, or is it just like a W? Like does that have
Omega,
Okay.
that's how you usually see it. So again, all lowercase letters.
Why don't we use capitals?
Well, the Greek alphabet, some of the capital letters look the same as the English capital alphabet. For example, A and B, I think look exactly the same. So we have the same problem.
Interesting.
But some of the letters look completely different. Like delta, that's another Greek letter.
Yeah.
Looks kind of like a lowercase d. It's a little different, like capital delta. I think it's a triangle, capital delta. So yeah, they just have a few different symbols.
Oh wait, isn't the delta stands for like change in
Yes.
physics or,
Yeah.
or math?
So sometimes when I talk about slope, instead of writing like y2 minus y1 over x2 minus x1, I'll do this.
So the change in y over the
Change in y over the change in x. Yep. And that's a Greek letter. I don't usually explain that in Algebra 1, but that's what it is. So I told you that when you draw an angle, there's usually a way you want to draw it, so it makes finding the initial and terminal side simple. And the way we usually draw it is what's called standard position. An angle drawn in standard position means that the vertex is at the origin and the initial side is on the positive x-axis. So it gives us kind of a uniform way to draw an angle. So if I ask you to sketch a 45-degree angle, everybody's would look something like that. It's not like some people would have it rotated, flipped. If it's in standard position, they're all going to look like that. Now, if I do this, it is that standard position. Why? What's wrong with it?
It's not a origin.
The vertex isn't at the origin. The initial side is good. It's on the positive x-axis, but it wasn't at the origin. How about if I rotate this and put that like that?
No.
No. What's wrong now?
The initial side is not on the x-axis.
Right. The initial side isn't on the positive x-axis. The terminal side is on the y-axis, but that doesn't have anything to do with standard position. So, initial side on the positive x-axis, vertex at the origin, just like that. And this would be your terminal. Any questions on what it means to sketch an angle in standard position? Okay. So one way that we can measure angles is in degrees. If you take calculus, it's not the most common way. In fact, degrees is not really used in calculus. Does anybody know another unit we can use to measure angles? Yeah? Not quite. It kind of sounds, well, that has a lot of letters in common with that. Yeah? Radians. Radians. So we're going to talk about how do we change between degrees and radians. And for calculus, like, that needs to become automatic. You have to be able to say, okay, 60 degrees, pi over 3. Like, it's almost memorized. I'm going to teach you. So, you have to know how to change between degrees and radians very fluently. So we'll look at both. But let's just talk a little bit about degrees first. If you had one complete rotation, how many degrees is in one rotation?
360.
Right? 360. Now, we can rotate two different ways. Clockwise rotations are positive. If you rotate in a clockwise direction, it's positive. I might even write this down. I think I wrote this down below. Oh well. I'll just write it down. Clockwise rotations are positive. What do you think counterclockwise is?
Negative.
Negatives. Counterclockwise. Clockwise are positive. Counterclockwise is negative.
So should I say negative for the 30 and 60 degrees below? It's counterclockwise.
So wait a minute, did I write that wrong? Clockwise, hold on, counterclockwise. Okay, let me fix that. That's kind of a big mistake. Counterclockwise is positive. Counterclockwise is this way. That's positive. Negative is when you go clockwise. That would be negative. This is correct. So one complete rotation in a counterclockwise direction would be 360 degrees. So one complete rotation counterclockwise is 360. How about one complete rotation clockwise? Well, that would be a negative 360. Okay, and I can actually show you what that would be. Right, so in this diagram, we can move the terminal side wherever we want to put it, but we can't move the initial. So if I go all the way around, one full revolution, I get an angle of 360 degrees. If I go beyond that, well, the angle just keeps increasing. So your angle can be as high as you want. We generally prefer to work with angles between 0 and 360. That makes it simpler. So let's go back to 0. And now let's go clockwise, one full rotation. And that's negative 360. Right, so positive and negative just controls the direction you rotate it to create an angle. So what about if I did a half counterclockwise revolution? How much would that be? It'd be positive, and it's only halfway around, so it's 180. How about a quarter?
90.
That'd be 90. So I already said that to you. So angles measured in a counterclockwise direction are positive. So CCW is positive. That's what we had here. And clockwise is negative. That's what we had right there. So angles can get larger than 360. That doesn't really happen when you're talking about polygons, right? Let's say specifically about triangles. Triangles all add up to 180, so you're never going to have an angle larger than 360. If we're talking about angles that are larger than 360, we're probably not talking about a triangle. We're talking about maybe a type of rotation. Right? So let's look at two different angles. Let's go like this. So there's 90. I want you to notice where the initial and the terminal side is right now. Okay, everybody got it? Now, let's do 450. How do the initial and terminal side compare now to where they were at 90?
They're the same.
They're the same.
Yeah.
The initial side and the terminal side are exactly the same for a 90 degree and a 450 degree angle. What that means is those angles have the same initial and terminal side, so they are called coterminal. So angles with the same initial and terminal sides are called coterminal. There's an infinite amount of coterminal angles for any given angle. What do you think the pattern is if I wanted to get the next positive angle that's coterminal with 450?
You add 360.
I add 360 to it. You get 810. That's the next positive angle that is coterminal with 450. Now, if I had to do a problem involving an angle 810 degrees, for most things that we do in trig, any angle that's coterminal with 810 could be used to do the problem. I would rather not use 810. I would rather make it smaller. So what do you think I could do to make that angle smaller instead of bigger? and it will still be coterminal. I can subtract 360 as many times as I need to. So 450 is a little better, and 90 is even better. Okay? Dealing with a 90-degree angle is a lot easier than 810. And for trig, those two numbers are the same, 90 degrees and 810, because they're coterminal. So the idea is to find coterminal angles, you can add or you can subtract 360. I would do the same thing if you gave me a negative angle. You said negative 1,000 degrees. Well, negative 1,000 means you went around more than once in a clockwise direction. I would rather work with an angle that's positive between 0 and 360. So I can add 360 as many times as I need to. Alright, so they want us to, for this problem, make a sketch and find an angle that's coterminal with the one I give you, that's positive, and then find an angle that's coterminal and negative. Alright, 30 degrees. So initial side, you're going to put that on the positive x-axis. And where would the terminal side be if it was 30 degrees, roughly?
Close to that. And quadrant 1 would just be
So like right in the middle of quadrant 1?
No, closer towards the starting.
Yeah, closer to the initial. It'd be 1/3 of the way through the quadrant. The quadrant is a 90. So you're just going to estimate it. Maybe about like that. All right, and let's find an angle that is coterminal and positive. What's an angle that is coterminal with 30 degrees and positive? Yeah.
390.
390. What's an angle that's coterminal and negative?
Negative 330.
Negative 330. Good. Right, let's do 145.
Sorry.
390 and negative 330. Okay, 145. Where's my terminal side going to be for that one? All right, we'll start with that. It's going to be in the second quadrant. Closer to 90? Closer to 180? Yeah, it's a little closer than 180. 135 would be right in the middle of 90 and 180. So 145 is 10 degrees past the center. So maybe like that. So there's 145. What would be an angle that is coterminal and positive with 145? So we add 360 to that, and we get how much? 505. And then if we want an angle that's coterminal and negative, subtract 360. Negative 215. And you could subtract 360 again too. But I'm just doing the first one I get. Question on that? All right, I'll do this one. Negative 45. Where's my terminal side going to be for this one? Let's start with the quadrant. It's going to be in quadrant 4. Closer to the horizontal, the vertical, or right in the middle? Right in the middle. There's your angle. Okay, so coterminal and positive. $315. And how about negative?
Negative 405.
Negative 405. questions on it? Okay, a couple terms that we use to describe angles. Acute. What does it mean if an angle is partially less than 90? I can think of an angle that's less than 90 that's not acute, though. What else does it have to be? Right, we have talked about negative angles, right? That's when you rotate the other way. So when we talk about acute angles, it's got to be between 0 and 90. All right, let's do the next one a little different. What if it's exactly 90? That's a right angle. What if it, well actually, let's do it this way. You tell me. What's an obtuse angle? And less than 180. Because if it's exactly 180, what do we call that? It makes a line, but there's a name for that angle.
Isn't it a straight angle?
That's a straight angle.
Sorry, can you show what you put for acute?
Between 0 and 90. What about complementary angles? Now we're not talking about one angle, we're talking about two. We're talking about a pair.
They add up to 90.
They add up to 90, and something else about them. Because I can think of two numbers that add up to 90, and it would not be complementary.
They both have to be between 0 and 90.
Right, it has to be acute angles that add up to 90. What does that really mean? They have to be positive angles. Negative 10 and 100 are not complementary. So two acute or two positive angles that add up to 90. How about the other type that you usually study? These add up to 180. That's supplementary. Again, same deal, has to be positive. 200 and negative 20 are not supplementary. I already told you that. Negative angles do not have complements or supplements. Right, so I'm going to give you a couple angles. Let's see if we can find the complement and the supplement. All right, 48 degrees. What would be the complement? 42. And supplement? 132. You just have to add 90 to the complement. So 132. How about negative 18? What's the complement? There isn't. Doesn't apply. How about the supplement?
Still also.
It doesn't apply. It's not applicable. So no complement or supplement. How about x degrees? And I have to tell you a little bit about x, because if, let's say, x was 100, well, then it wouldn't have a complement. It's too big. So let's say x degrees and x is some number less than 90. How would you find the complement of
90 minus h.
90 minus x? You might say, well, wait, what if x is bigger than 90? It's not. How about the supplement? 180 minus x. So that's kind of a general formula for finding the complement and the supplement. 90 minus your angle is the complement. 180 minus it is the supplement. Any question on that? Okay, so last thing. So another way that we can measure an angle is in radians. And if you look at the word radian, it has a lot of letters in common with the word radius. And I'll tie those two together in a minute. But a radian is another way to measure an angle. So look at that picture. So what I've drawn here, it's called a central angle when you put an angle in a circle. And this is angle ACB or BCA, either way. CA and CB are radii coming from the center of the circle, and they hit the circumference, or they hit the perimeter here and here. Between A and B, that's called an arc. Now, something special happens in a circle if this was exactly 1 radian. So if you drew an angle that was exactly 1 radian, and that's almost the scale of what it would be, the length of this arc in red and the length of that radius would be the same if you had an angle that was 1 radian. So that's kind of a visual you can think about when you think of a radian. An angle of 1 radian is an angle that when put in a circle, the length of the arc is equal to the length of the radius. And that doesn't always have to be true, because imagine you put an angle like this in the circle. Well, now the length of the arc is extremely short. The radius is the same. But this angle is a lot less than 1 radian because the arc is a lot less than 1. It's a lot less than the radius. And the arc could also be bigger than the radius if you made a really big angle. But that's the idea of how you can picture a radian. It's an angle that when drawn in a circle, the arc length is equal to the radius length. It doesn't really tell you how to convert between degrees and radians. It just gives you a picture in your head of what a radian looks like in a circle. Any questions on that idea? And that's kind of a nice fact to know, because if this is a 1, it automatically means 2 lengths in this diagram are equal. And the fact that 2 different lengths are equal in that diagram, we can use that to figure out the sizes of other arcs in this circle, based on the fact we know this arc and this line are exactly the same if the angle is 1 radian. So we could kind of scale it up. If it was 2 radians, we could figure it out from there. But we're not going to talk about lengths of other arcs, but keep this fact in mind, and we will come back to that. All right, so how do we convert between radians and degrees? That's the important thing for the end of this. How do we convert between the two? Well, to convert one thing to another thing, all you need to know is one connection between the 2 things. It can be any connection at all. For example, let's say I want to change feet to inches. Can somebody give me a fact that is true that relates feet to inches? It can be any fact at all. Okay, so 1 foot is 12 inches. Now, let's say I want to convert 36 inches to feet. Since I already have a fact that's true, all I have to do is fill in 36 on the other side, cross multiply, and I can solve. But the key is you had to already know that. You could have also said in 2 feet is 24 inches. That fact works fine. The simplest fact is the best one. But any true fact will work. Now, just because I used originally a 1 and a 12, does that mean I can only put a 36 here? No, I could put a 38, a 42, or a 57.9 if I wanted. I can put anything here. Just because I picked these 2 numbers, it does not limit what I put there. This was just a true fact to start with. So what we need is a true fact to start with. If we wanted to convert between degrees and revolutions, I think you guys already know the fact that's true there. One revolution is 360 degrees. So if you wanted to know 5 revolutions, you could cross multiply and solve. But I'm more interested in converting between degrees and radians. That's what I need to figure out. So no 1 revolution equals 360 degrees, which equals, that's what I want to figure out, how many radians in 1 revolution. So we're going to look at this diagram. Okay, this diagram is a circle, and it's called a unit circle because I specifically labeled the radius as 1. Anytime you have a circle with a radius of 1, it's a unit circle. There's something very special that happens on a unit circle, and we can use that special fact to help us figure out the connection between degrees and radians. Now, just because I'm using a special circle to figure this out doesn't mean I can't generalize this. Just because I use 2 special numbers here doesn't mean you can't generalize it and put whatever you want over here. It's going to be the same idea. We just need to figure out some connection between degrees and radians. Any connection on any circle, just something. Okay, we need something. And this is the fact we're going to use. In a circle of radius 1, what happens is that if you measure the angle in radians, it comes out exactly equal to the length of the arc. So this is a unit circle. Let's say I draw this out, and that's 1 radian. Then this arc is 1 unit. If this angle is 2 radians, then this arc would be 2 units. If it was 7 radians, 7 units. 8, 8, 10, 10. They're always the same on a unit circle. So the measure of the angle is equal to the length of the arc. So let's think about this arc. How much of the circle does that arc take up? A quarter. How about that big of an arc? That big of an arc? How about that big of an arc? Now it's an arc that's so big it takes up the whole thing. We don't really call it an arc anymore if it takes up the whole thing. What do we call that?
Circles.
What about the circle?
Circumference.
It's the circumference.
Oh, yeah.
If we can find the circumference of that circle, the circumference, which is an arc, is equal to the radian measure of the angle. So if we can find the circumference of the circle, that's going to be the same number as the size of the angle that would go all the way around the circle, because these 2 numbers match. So what we're going to try to find is that number. We're going to try to find the length of the circumference, and that's going to tell me that number, which is the size of the angle that goes all the way around the circle. And that's what I want to know. So what's my formula for circumference?
Is that the pi r squared? No.
That's area.
Right.
2 pi r.
2 pi r. Now, what is the radius specifically in our circle? 1. So what is the circumference of our circle? 2 pi. So we just found the circumference of the unit circle. That's the length of the arc. What is that the same as? It's the same as the angle. The arc and the angle are the same. So if the arc that goes all the way around the circle is 2 pi, What's the number of radians to go all the way around the circle? 2 pi. So now we have a connection between how many degrees go all the way around a circle and how many radians go all the way around. There are 360 degrees in 2 pi radians. The only reason we were able to get that is because of this special trick with a unit circle. But we needed something, so you wouldn't have known this probably if I didn't tell you, but I had to give you something to figure it out. All right, so actually that's what I wrote up above. 1 revolution is 2 pi radians, which is 360 degrees. Yep.
I'm not sure if you're about to get there, but would that mean that 180 degrees is just pi?
Yes. So 180 degrees would be pi radians. Now, it's fine to write a relationship like that, but usually when you give somebody a connection between 2 different things, there's a certain number that's in the connection. And what number is it? Yeah? It's usually 1. Like if I asked you how many minutes in an hour, you wouldn't come back and say that there's 180 minutes in 3 hours.
No.
Well, okay, you've answered my question, but you didn't really give it to me as simple as you could have. 60 minutes in 1 hour. 24 hours in 1 day. Yeah, whatever it is. But the number you usually have in a conversion is a 1. So let's get a 1 on one side of this. Which one do I want to do first? Okay. Let's get a 1 on this side. How would I get a 1 on the right side? Divide each side by 180. Not 180 degrees, just 180. So now it says pi over 180 radians equals 1 degree. So if I wanted to know what that is as a decimal, I could do the pi button on my calculator, divide by 180, and that would be 1 degree. What if I wanted to know 2 degrees? What could I do to both sides of this equation that would give me a 2 over here instead of a 1? Multiply by 2. Multiply by 2. So now we have a formula for 2 degrees. What if I wanted to know 5 degrees? How could I get a formula that would turn 5 degrees into radians? Multiply both sides by 5. Now it says 5 degrees. 5 times 1 is 5. 5 degrees equals, and you have a calculation you could do out. The point is not what number you put in this box. It's the pattern. Whatever number you put in this box gets multiplied by what? Pi, and divided by what? 180. That's how you convert degrees to radians. To convert degrees to radians, you multiply by pi, and you divide by 180. Now, let's go back to our formula one more time. So multiply by pi, divide by 180. Let's look at it again. This time, how could I get a 1 on the left side? Divide by pi. Divide by pi. So now it says 1 radian equals 180 over pi degrees. So it's like 57 roughly. What if I wanted to know how much 2 radians equals? How could I modify this equation? Multiply both sides by 2 and by 2. Again, the point is not what's in the box, it's the pattern. To change a radian into a degree, you're going to multiply by what number? 180 and divide by pi. So to convert from a radian to a degree, multiply by 180 and divide by pi. Now, it can be a little tricky to remember which way is which, because one's multiplied by 180, one's divided by 180. But if you can remember something I'll show you, you don't have to even memorize which way is which. All you have to remember is when I say 180, I want you to think degrees. So I want you to make a connection between those two things. Degrees, think 180. Degree symbol, think 180. Pi, radians. So when you see radians, think pi. Pi goes with radians. 180 goes with degrees. If you remember that, it'll take care of remembering all of that for you. So think degrees, think 180. Your radians, think pi. Let's convert this to radians. We're either going to multiply by pi over 180 or 180 over pi. It's always one of those two. But think about 30 like this. You have degrees in the top. Where would degrees have to go to cancel out?
The bottom.
The bottom. Degrees is in the bottom, which means the other unit is in the top. When you think degrees, what number always goes with degrees? 180. And what number goes with radians? Pi. Degrees in the top and bottom cancel. 30 goes into 180 6 times. So what do you end up with in the top? Pi over 6. And you might think I left something off that answer. I didn't. When you see radians, the word RAD is usually not there. So how do you know if it's radians? There's only 2 units we use, radians and degrees. If it's a degree, you'll see the little circle. If you don't see the little circle, then you know it's a radian. Right? How about this one? What unit would go in the bottom? Degrees.
180.
Pretend radians is in the top, it's invisible. But what number goes with degrees?
180.
What goes next to the RAD? Pi. 45 goes in once. And how many times does it go into 180? 4. So 45 degrees is pi over 4 radians. That's good. Let's try this one. Convert the other one. For this one, I'll write it. Pretend the RAD isn't going to be there. You've got to get used to not seeing it. Where do you want RAD to go? We want to cancel it because we want to get degrees. So rad in the bottom, degrees in the top. What number goes with degrees?
180.
What number goes with radians? Radians is gone. Pi is gone. And 2 goes into 180 how many times? What's 3 times 90? 270. And what's the unit on my answer? Do I need a symbol?
Yes.
Yes. If I don't, that's 270 radians. Now it's degrees. Do one more of those, then I want to do one where we round. I thought I had a round one. All right. Let's do 2 pi over 3. What are you going to multiply by to convert to degrees? 180. Divide by pi. Pi's are gone. 3 goes into 180. 60. 2 times 60
120.
is 120.
Degrees.
Degrees. And let's do one last one where we round. Find the degree measure of 3 radians. And I erase RAD because we got to get used to not seeing it. We're converting 2 degrees. What's going to go in the bottom? Pi. what's going to go in the top. When you want to do it as a decimal, this is how you should do it. 3 times 180 divided by the pi button. It's divided by pi. It's 171.89. Why do you think I said use the pi button and not 540 divided by 3.14?
Because
Isn't
no,
it
it's
really
accurate.
off of it?
Yeah, we're going to be off. If I'm looking for an answer to 2 decimal places, 89 and 97 are very different. So always use the pi button when it asks you to round.
Can you show the first example problem for
Yep, I can. Let me just
scroll up?
let me just put up the homework for people to copy first, and then I can scroll down.
Okay.
So a lot of these questions are very quick. Like find the complement, find the supplement. Is it acute? Is it obtuse? Is it a right angle? They're very, very quick questions. So we covered like 7 or 8 different things about angles and rays and stuff today. So I gave you like 3 problems on each type of thing we did. So reminder that test is tomorrow. I'll be after school, and I'll get the study guide up right after you guys leave and go to lunch.